Okay. Well, morning, everybody. Hello to you people on the video. If you're watching on video, great to see you all as usual. So today we're on to chapter 8 stuff and torque and all that. Just quickly, we do have our ed reader today, volunteer. So thanks very much to you for that. If you want to type something in, Raphael has the microphone, but anybody else just wants to shout loud enough, I'll also hear that. So that's still allowed. So next slide, just be warned. Okay, might be a little jarring. It's this one. So this happens in early November. Is University of Toronto posts its final exam schedule. So one thing to keep in mind is that I don't run the final exam. I am just an employee there who kind of helps invigilate. Say again? Yeah, so what I do is I make the final exam, I give it to these people, they do all the actual, invigilation as it's called, they deliver it, they deal with everything, and then they give it back to me to mark it. So I'm not officially involved, but it is going to be my task. I am going to be running around all these rooms on that day trying to just pop my head in, but as you can see, you're going to be spread out all the heck over campus. So from my point of view, you might not see much of me during the test, but there will be certainly some TAs from Physics 131 in the room at all times, and they'll have my cell phone number if anything real bad's going on. So you got to be there. And the thing about this one is that with conflicts or anything like that, you have to deal with the faculty registrar's office. You can't deal with me, because again, I'm not running it. So you got a conflict, let them know. They define a conflict as I think 2 exams that are overlapping. That's obviously a conflict, because you can't be in 2 places at one time. But also I think if you have 3 final exams in one day, that qualifies as a conflict, and they will try to reschedule you for one of them. So take a look at all your exams on this website. Make sure you know what you're doing in December. You'll have 3 hours, and it'll be basically a double term test. Same exact format, except instead of 10 multiple choice questions, there'll be 20. Instead of 1 written answer, there'll be 2. Simple. So you're going to have to actually fill out 2 sheets, I guess, but keep it simple. And it'll be the whole course from chapter 1 through 11. Okay. How are we doing at that discussion board? You're good? Everybody good? Want to get going on chapter 8 stuff? Let's do that. Yeah, so I actually feel chapter 8 starts off just it's a little hard for me to follow when she introduces torque. So let me go over a bit of the big picture with both chapter 8 and chapter 9. Big idea here is that so far, you've been doing this particle model of things and just considering translational motion, either one-dimensional, like along the x-axis, or two-dimensional, where you have an xy axis. So you're still doing that, but now we are introducing the sort of extended body model. So you can do an extended body force diagram instead of just a regular force diagram where you do a dot with all the arrows coming off of it. Now you actually draw usually a rectangle or something, and then you draw the forces coming off of that. So all this stuff we've done before, force, momentum, energy, that's still important, but now we've got some extra things, which are torque and rotation. And they're sort of intertwined, so I want to talk about both. But yeah, this is... she also says extended body, she says rigid body. So it just means something that doesn't change its shape as you apply forces to it. So like the distances between all the points on the object remain the same, and it remains the same orientation, but you can rotate it as well as move it. So I've got this wheel. Hopefully you can sort of see that on the video. But on the wheel, I have put a piece of orange tape and this is more a chapter 9 concept, but basic idea is you start from the x-axis and go up. The tape moves some distance as this thing rotates. It'll do a circumference if it goes all the way around, right? And that distance is sometimes called s. And you can find s and how it relates to theta, which we call rotational position or something, by this equation. S equals r times theta, which works if you've got theta in radians. Reason for that is that there's 2 pi radians. By definition, there's 2 pi radians in a full circle, and 2 pi r is the circumference of the circle. So you're kind of doing a fractional distance there. So, okay, so imagine we were to plot distance versus time, then we could do the slope and get the velocity, right? So that's kind of what we're going to do. It's in calculus, we call it a derivative, but in this class, we just sort of more take it as a slope. This is the time slope, or slope versus slope of a position versus time graph becomes a velocity. So what you've got is at any moment of time, this piece of tape has a tangential velocity, which is that it's usually a green arrow in textbook, and that can be found from what's called, that's a little omega. Maybe I should. It looks like a W, but on MyLab and Mastering, it's actually a Greek letter omega. So you have to do a pull-down menu and get the omega out. It's the last letter in the Greek alphabet. That is sometimes called the rotational velocity or the angular velocity. This textbook calls it more the rotational velocity. She puts angular in brackets. But anyway, whatever omega is, if it's going slow, then omega is low. If you speed it up, then omega is high. So you can imagine plotting omega versus time and doing the slope of an omega versus time graph, and that's where you get this thing called alpha. Again, this is a little bit of chapter 9 stuff, but I'm going to bring it back. There's a reason. It's all going to be related to torque. So what's alpha? Well, I guess you could look at the tangential acceleration of this thing if it's speeding up. So maybe it starts slow, but getting bit by bit faster and faster and faster and faster because I have some outside torque. So what I'm doing here by hitting this is applying a torque. You could also, I guess, slow it down by putting frictional torque to slow down and get a, I guess, but anytime the omega is changing, you've got this alpha thing. And alpha times r is the tangential acceleration of this guy. So, and these are like the graphs. So if you graph theta versus time, slope of the graph is omega. If you graph omega versus time, the slope of the graph is equal to alpha. And I guess you can find the meters per second by just multiplying by r in each case. I'm going to come back to that, but so basically there's an analogy here between what we've already done, x and v and a, position, velocity, and acceleration. That was all linear in meters per second and all that. Now you can kind of analogize with theta. You just sort of basically go to Greek. So what I've drawn here is kind of like a rotational analogy where everything on the left, which we already know, kind of has an analogy over on in the angular space or rotational stuff. So, yep, question.
We have a question on Ed here. The question is alpha the same as centripetal acceleration?
Yeah, no, that's a great question. Let's go back quickly here. I did put centripetal acceleration here. That's what this thing is. Centripetal acceleration is AR, and that's not the same as alpha. It's a bit confusing. Centripetal acceleration is any time something's on a curved path, even constant speed in a curved path, it's accelerating towards the center. That's different than alpha, which is when the thing is actually speeding up. So alpha is 0 if you have uniform circular motion. And it's only if omega is changing that you get this alpha thing. So that's a great question. Good point. So if you've got alpha and it's changing, that means that it's accelerating sort of in the tangential direction. And so you need a force in order to give an acceleration. Acceleration comes from force divided by mass. So to have the thing have an alpha, so it's speeding up, like not uniform circular motion, you just got zero torque. It'll just go like this forever if there's zero torque. But if you want to slow it down or speed it up, then you need a torque. And so the angular acceleration alpha is equal to the torque divided by something else that's analogous to the mass. So mass has its analogy, which is called rotational inertia. Some textbooks maybe call this AKA moment of inertia. It's a chapter 9 concept really, but I think I'll just throw it in there. That's analogous to mass, and then torque net is analogous to the net force. So the sum of all the forces divided by the mass gives you the linear acceleration. The sum of all the torques divided by the, whatever this thing is, rotational inertia, which is a capital I, gives you the analogy to accept the angular acceleration. Okay. So that's sort of an overview of all of chapter 8 and 9 and where we're kind of going with this. And now I'm going to go back to the beginning of chapter 8 where she kind of goes through it a bit.
We have another question.
A bit more carefully. Yep.
Oh, now we have 2 more questions. The first question says, "Hi, Professor. Could you please upload the previous slides on Quarkus by any chance? They are not on our class notes." That is what the questions. That is one of the questions.
I'll verify that.
Sorry.
Yeah, I'll go check that. That sounds good.
And then the other question is, where can we find the slides that are being shown right now? I don't see them in today's presentation slides.
Well, there's sometimes I post the pre-class slides, which they're not always very complete. So these last slides I showed, I didn't put them on there yet. So sometimes I make last-minute changes, and I realized that chapter 8 doesn't really tell you this thing about what torque is, so I threw these in. But they'll be posted by about 2 o'clock today.
All right,
I'll check
perfect.
yesterday's
That's
notes.
all the questions for now.
All right. Good. Okay. Keep me on my toes. So back to chapter 8. There's an axis of rotation. When objects turn around axis, physicists say that they undergo rotational motion. And a door is a good example. The hinge of the door is called the axis of rotation. And then if you open the door, really what you're doing is you're rotating that door about the hinge. And when you cause rotation, you need a force. And so there's different ways you can apply a force to the door. You can imagine that if you apply F1, it's not going to really open the door. You're going to push on the hinge, and it's not going to swing the door. F3, if you're pushing right sort of towards the hinge, like that's the wrong way to turn the door as well. What you want to do is something like F2, and that'll rotate it more easily. So this is our first concept of torque, and there are 3 things to consider when you consider torque. One is the place where you exert the force. That's important, and it never was before. When we drew force diagrams, we just usually did a dot. But now this is the new thing, is that the place where the force is exerted. And the other 2 things are magnitude of the force and the direction, which you're pretty used to considering. Okay. Let's do the first learning catalytics question. It's a multiple choice. Try to pick the force that is most effective at opening the door. So biggest magnitude of the torque. Give you a minute to think, pair, share. Move on. You assume they're all the same magnitude force in each case. Just different direction and different place. Holy smokes. Okay. So, going once, going twice, and survey says, any more responses? Interesting that there's 339. Remember when these numbers used to come in at around 600, so I can see. I need to encourage people somehow to maybe come forward a bit. But this is a one where your intuition kind of helps you, I think. What would be most effective at opening or swinging this door? Clearly, if you just push right along the hinge, it's not going to swing it one way or the other. But these forces are all going to turn it kind of counterclockwise. And which would be kind of best at doing that? Well, my gut feeling is that F1. You want to be far from the hinge, and you want to be perpendicular to that, I guess, line from the hinge. It's far. So the angle also is important from rotation axis. And so the angle is going to be important, perpendicular to the line from the rotation axis. So I asked you last time, why is it better to put the handle on the opposite side of the hinge? So don't put it in the middle of your door, even though it might look kind of symmetric. Torque is the rotational analog of force, as we talked about before. Force causes things to accelerate along a line. Torque causes things to have angular acceleration. And that's what you need if you're going to open your door. And torque comes from force times what we're going to talk about is lever arm. Lever arm is the distance between where you apply the force and the hinge. Maybe I should say the perpendicular distance. I'm going to go over that a little bit more. So perpendicular distance, or the component there. Putting your handle further from the hinge increases the lever arm, and therefore it increases your torque for the same applied force. So maybe Pius, can you help me out? And it's ox plate, right? I'll hit ox plate. I want you to, can you undo one of those? Because I don't know which one comes off. So Pius is applying a torque to undo one of these nuts. I think all these bolts are in so tight, and you'll see why in a minute. Can you undo? You can't. Oh, there. You can't quite do it. Let me see if I can do it. I know you're very strong. Okay, so this is, that was the joke, is that I'm now applying a much greater torque, although now the bolt is totally stripped, so doesn't matter how strong you are. But the idea is that with the same force, I can now use a wrench that has a much larger lever arm, and that's the idea of this demo, is that now I'm applying a much bigger torque, and the torque is what you need to get these bolts off. And you need to not have stripped your bolts. So they're all stripped. And this, by the way, is called a torque wrench. So you can actually, as you're turning something, this will measure I don't know if you can sort of see it there, the foot-pounds, which is foot being distance, pounds being force. Foot-pounds is force times a distance. And so it's the force times this lever arm distance. Okay. Awesome. All right. So there it is. That's the equation that comes from your textbook, and it just couldn't look more confusing. But certainly you get the SI unit of torque is the Newton times meter. I'll put some little comments on here. This, of course, is the Greek letter tau. T-A-U. What else is there? So what you end up with here is a force, which has some vector, and some other vector, which I'll talk more about, called L. And in between F and L, there's an angle, theta. So F is the magnitude of the force. L is the magnitude of the distance between, so here's an axis, rotation axis. Here's an object, and here is maybe a force. We'll call it F. Okay. Then what you do is you define a distance here, a vector L. Okay. And then this theta sort of comes from there. And this plus or minus is by historical convention, which we'll use in this class, plus tau is counterclockwise. So you have to draw a diagram, kind of look at it, and if the torques are going counterclockwise, we say they are positive, and then minus tau is clockwise. You may ask why that is, and I think that's because, remember when we did theta, we measured it from the x-axis up towards the y-axis, and that was positive change of theta, and so that's the counterclockwise direction. So to sort of keep it all consistent with that, we made counterclockwise be always the positive thing. How's it going on the discussion board?
There is a new question. It says, if our test was regraded on Gradescope, when will our mark be updated on Quercus?
Oh, I don't know. Yeah, I have to re-import the marks. It's another good thing to note. So,
I also have a question that is not on here that I'd like to ask myself. If that's
yes,
okay.
please, yeah.
For all the iPad kids in the class like me, which way is counterclockwise and which way is clockwise again?
Yeah. So the clock starts at 12, tick, tick, 1 o'clock, 3 o'clock, 6 o'clock. So this is clockwise. And then counterclockwise is the opposite way. So I always try to think of the second hand on an actual clock and which way it tends to go.
Perfect. Thank you.
All right. But yeah, I'm going to have to go through the discussion board and try to deal with some of these specific things as they come in. All right. Torque wrench, Newton meters, foot pounds. Let's do an actual example, shall we? Doing pretty well for time here. Lewis uses a 20 centimeter long wrench to turn a nut. The wrench handle is tilted 30 degrees above the horizontal, and Lewis pulls straight down on the end with a force of 100 newtons. So I'm going to try to draw this out. Here is what he is trying to turn is a nut. And that's going to be the rotation axis. And the more torque, the more it's going to turn. And then we can try to draw the wrench. Sort of goes up like this. I don't know how to draw a wrench, but there's a force, F of Lewis on the wrench, down. And there's an angle here of 30 degrees. It's a terrible drawing, but you get it. And then there's a distance here from here to the rotation axis of 0.20 meters, 20 centimeter long wrench. And we're going to find tau. And I guess the system, in this case, is going to be the wrench plus the nut. They're kind of attached. And then he's going to apply torque to the wrench, and if the nut is not stripped, it'll turn the nut, and they'll turn together. So now we draw the extended, it's called the extended force diagram in the simplifying diagram step, which is you draw it again, but now you draw it as sort of a rectangle, something easier to draw. And there's your F, and there's your axis. Should label your rotation axis. And we're going to use equation 8.1 which is tau is equal to plus or minus FL sine theta. And I can draw them out here. This is your L. Oh, I didn't draw that very well. There's a 30-degree angle here, right? So let's draw it a little better. If this is horizontal and this is L, then this is 30 degrees. And then your force, if you connect these two vectors tail to tail, then this angle is the theta. This is theta. So in this case, theta is actually equal to 30 plus 90 degrees. So it's equal to 120 degrees. But anyway, what I get is tau is equal to, it's 100 newtons times 0.2 meters times the sine of 120 degrees. I'm just doing absolute values for now. I got 17 newtons meters. And then direction, I'm going to tack on a plus or minus sign based on the direction. The direction's counterclockwise. So therefore, tau is equal to plus 17 newtons times meters. So what I do in practice is I use this equation 8.1 to find the magnitude of the torque, and then I use my diagram to find if it's clockwise or counterclockwise, meaning if it's negative or positive. Yep. Did I say the angle has to be in radians? That's a really good question. I did say the angle has to be in radians when you're doing things like angular acceleration. But in this equation, it's in degrees. So in chapter 8, we still use degrees. I think that when you use radians is when you're trying to actually keep track of something that is spinning around a lot.
We have a question.
If it was given in degrees, then it's going to be degrees. Yeah, and a question from discussion board?
The question from the discussion board is, could you have drawn the wrench on the right side and put angle theta on the right, or would that mess up the calculations?
Yeah, no, you get the exact same answer. I've just put it on the left side because that's how I drew it. But yeah, you get the exact same answer. You put it over on the well, I guess you'd get negative, wouldn't you? Okay. But you'd still be correct. So I assumed it was on the left side. Another excellent question.
We have another question on the board too.
Yes?
Why is it counterclockwise? That is the question.
Because I assumed it's on the left.
Okay.
Okay. So let's just put here, assume wrench is on the left. So if you assume wrench is on the right, then you get clockwise. So sometimes these questions are not really specified exactly, and so you make some assumptions and you get a different answer depending on what your assumptions are, which is fine. That's like life. Make some assumptions at the beginning. And just to repeat, the sign convention for torque is that it's negative torque if it's trying to rotate something clockwise, and it's positive torque if you're trying to rotate it counterclockwise. Okay. So I see if the torque tends to produce a counterclockwise rotation, that's positive. If it tends to produce a clockwise rotation, then it's negative. All right, let's do some related learning catalytics questions. A ladder leans against the wall. So I'm going to draw the normal force of the wall on the ladder right here. This is a force, NW on L. What's the sign of the torque? Is it positive or negative, or is it zero, or does it depend on where you choose the rotation axis to be? Give me a minute to think about that. And then I got some more questions about this exact same ladder. You guys got an answer for me? This might be a bit of a trick question, but there's a point. Going once, going twice, and stop. And survey says, sorry guys, that's what I was going for there. Remember, you still get the 0.8 just for answer right. Definitely depends on where you choose rotation axis. So when you set up your question, you're going to get different torques depending on, what was our other assumption? Oh yeah, how you assume the wrench was. Also, where you put the rotation axis, right? And in this case of the ladder, it's not rotating. So you choose where to put the rotation axis. So when an object is not rotating, if it is rotating, or if it's a door or something that has an obvious hinge, when an object is not rotating, you choose the rotation axis. And you have to do that, or else you can't compute any torques. So it doesn't matter where you choose it. Although, usually there's a kind of better choice, depending on what you're trying to solve for. So, for this one, if you're trying to understand about the torque from the normal force of the wall and the ladder, that's way up there. If you choose the rotation axis to be there, then the torque will be 0. And you usually get something like 0 equals 0, and it doesn't work. So you usually, if you care about a particular torque, try to choose the rotation axis somewhere else, is my suggestion, based on doing a lot of these. So I'm going to choose it to be the foot of the ladder. So imagine that's the rotation axis. In this case, what is the torque? You guys can probably get this one pretty quickly. Let's see if we're thinking about this. Like some of you may have assumed this before. Yeah, it's a really good point. The ladder is not moving, but I think in my mind I have to kind of almost imagine it rotating about the rotation axis to understand which way the torque is. If this was the only force, then which way would it move? Okay, going once, going twice, and I've got 75% are voting for negative torque and 23% for positive torque. I think it's negative. Why? Yeah, because if the only force was this normal force of the wall on the thing, then it would tend to rotate it this way, about the rotation axis right here. So this is the axis down there. You imagine that's fixed. If the only force on the ladder was the normal force from the wall, that horizontal force from the wall, it would tend to pitch it in a tick-tick clockwise direction, and that's negative by definition. Seem okay? Rafael, do you want to check quickly what's going on with the discussion board?
Question on the discussion board. Thank you
Yep.
for reminding me. For the first ladder question,
Yeah.
what are the different options where you could place the axis?
Oh, yeah, it's a really great question. Yeah, so yeah, you could, if you had put the rotation axis up on the upper left side, which is another good place, then the torque is 0.
And another question just came in now.
Yep.
When is torque 0 is what the person
Yeah,
asked.
so torque is 0 when one of these three things in your equation is 0. Either force is 0, or L is 0, or sine theta is 0. So what's sine theta again? So theta is the angle between the force and that L vector. And so if that's 0 or 180, then you get sine theta is 0. So
Also, there's a question inside of a comment in another question.
yeah.
And it's under the question, why is it counterclockwise? And the question is, to clarify, part of the question, if there is a downward force applied in the wrench example, the wrench would finish in a position where the wrench handle is parallel to the applied force, right? And that is the question.
Yeah, that's a good point. If you're pressing down on the wrench at that angle, and then the angle goes to 90 degrees, I guess you end up increasing the torque. Let's do quickly another learning catalytics question. This is a different one. It's asking you, so again, I'm going to choose the rotation axis to be at the bottom of the ladder. So that's a choice, axis. And now in this case, what's the sign of the torque of the static friction force of the floor on the ladder? So we can draw two forces down here. There will be the normal force of the floor on the ladder. And there will be, actually this is a question, which way is the friction? I think it wants to slip to the right on the bottom. Does that make sense? If these were perfectly slippery surfaces, then I think the ladder would want to slip to the right, so therefore the static friction must be applied to the left. Does that make sense? What's your opinion? Oh, true, because yeah, you're either going to get theta or 180, 0 or 180. Or yeah. Yeah, actually, no, wrong. L is 0, yeah, okay. That's the thing. Yeah. There is no L. Never mind. Sorry, I always like to think about which way the static friction force is. And it's whatever force is needed to prevent the surfaces from slipping. And in this case, I think the bottom of the ladder has to have a force to the left to prevent it from slipping out to the right. I'm just going to give you 10 seconds to click in on this one, please. I mean, the question you always get on these physics tests, by the way, is they always ask you, what's the minimum coefficient of static friction to prevent the ladder from slipping? So we could do that if you want. But we'll do that after another. Let's talk about, because there's another thing going on here which we didn't talk about yet, which is gravity. Gravity is part of this that's going to be pulling down somehow on the ladder and causing it to want to fall. So let's talk about gravity. Let's first finish this up. Going once? Going twice? Answer I like here is 0. Reason being that the force is applied at the rotation axis. And anytime that's the case, you're not going to rotate the thing because your lever arm, your L vector there is 0. So does that make sense? Torque is 0. And that is because, as we said, it doesn't matter. The distance L between F and rotation axis is 0. When that if the force magnitude is 0, then torque is 0. If L magnitude is 0, then the torque is 0. Now, it doesn't mean that it's not important. The force is still important because you got to remember it's still a force. It could accelerate the whole ladder, right? So you have to, when you're doing these torque problems from chapter 8, you have to keep in mind that there is still x and y force. Net force in the x direction should be 0 if it's not accelerating left or right. Net force in the y direction should be 0 if it's not accelerating up or down. So you kind of have to remember all these chapter 4 things in order to do this. So, okay, center of mass. Basically, there's a special point on any object called the center of mass. And the very beginning of chapter 8 talks about pushing a heart shape on the floor with a pencil. And that if you find the place where you push it and it doesn't want to rotate, then, and you do that for different directions, you can find this center of mass. But honestly, in a physics problem, we're just going to tell you where the center of mass is. Or it's going to be kind of obvious. We'll say it's a uniform object, in which case it's at the geometric center. Anyway, if we're going to calculate the torque due to gravity, then we have to find where on the object to draw the force vector for gravity. So, which is kind of a mysterious thing. If you think about it, every single molecule in any object is being pulled by the force of gravity. So there's going to be like 10 to the 23 torques or something on an object that has 10 to the 23 atoms in it. But what we're going to do in this class is, when calculating the torque due to gravity, you may treat the object as if all its mass were concentrated at the center of mass. And that works. Or sometimes called center of gravity. So what we do in order to draw an extended force diagram that includes gravity is we imagine the gravity comes up with a little hook from the center of the Earth, I guess, and hooks onto the object and pulls it at its center of mass. Question?
I just got a question on the ed. It says, for clarification of the last learning catalytic, if the ladder is sliding to the right, wouldn't there be no static friction and instead be kinetic friction as the ladder is sliding?
Yeah, true. But with static friction, so yeah, if it was sliding, then there would be kinetic friction. But with static friction, it's as needed to prevent sliding. So for me to understand what direction static friction is, my personal trick is I always imagine, what if it were to slide a little? Then the force of static friction would be what's needed to prevent the sliding. Let's do one more. Let's do two more. Let's do a learning catalytics with this question. What is the sign of the torque of mg, which is sometimes called the Fg of the Earth on the ladder? And again, let's define the rotation axis to be the bottom of the ladder. Your first step is you have to draw the extended force diagram and draw your gravity force on there. And then, second step is think what happens if gravity was to turn it a little bit. Which way would that be? Clockwise or counterclockwise? If it was the only force. And then I think we should just solve this problem. We got some time, right? Got enough time to solve it. Ten seconds. Three, two, one. Is it positive or negative? Class is saying positive. 86% of you are voting for positive. That's the one I like as well. Is that if the only force was this mg, it would tend to rotate this thing counterclockwise, opposite the way the clock ticks. Okay, so now let's just do the question that we've been kind of leading up to, right? Which is, before we do that, let's quickly talk about the lever arm, because this is important. And then we'll do this question that's on your learning catalytics. The trick I'm going to use is lever arm. So if you've got an object like this, with a rotation axis, and there's L, and you're applying a force, F, then what you can do is draw a force line. Is the line that's parallel to the force and goes through application point. Pius, do you mind closing that door over there for me? I think so. Then the lever arm is this D. D is lever arm is the shortest distance from the force line to the axis. Okay. So that's a nice little trick. If your force is at the rotation axis, the lever arm will always be 0. If your force line goes anywhere through the axis, in any way, your lever arm is 0. And then you don't have to worry about these thetas so much. So going to this one, your slipping question, you can set the system as the ladder and choose the axis of rotation as we've been doing, the foot of the ladder. Your force diagram will look like this. Let's at least draw the diagram here so we can do this. So there's the ladder. What are the forces on it? So I can draw them out here. I've got a normal force from the wall, which maybe I'll call N1. And I've got mg acting down at the center. And I've got another normal force from the floor, which I'll call N2. And this static friction force Fs. So what we can do...
We have another Ed question. Sorry to interrupt you.
That's okay. What's up?
The question says, how would we deal with forces that apply a torque as well as an acceleration to an extended object? Will we get questions which need us to perhaps split the force into its torque-providing component and accelerating component?
Yeah. Okay. That's exactly what we're going to do in this exact example. Is what we're going to say is we're going to set that y equals up, x is to the right, this is the rotation axis, and we're going to say that the sum of the torques equals 0, the sum of the forces in the y direction equals 0, and the sum of the forces in the x direction equals 0. We have to use all three equations in order to solve this problem. But let me just quickly set this up. This D1 is 2 meters. This is the lever arm for like torque 1. Okay? And then the other distance here that's going to matter is this dg or something, which is 1.5 divided by 2 meters. And this is going to be the lever arm for gravity. So my whole strategy here is I'm going to set the torques equal to 0, but that's not going to be enough. I'm also going to have to set the forces in the y direction as 0, forces in the x direction as 0. You'll have 3 equations, and we can eliminate those normal forces, which are unknown, and eliminate, and I guess solve for mu sub s. Which, one more thing, don't forget, that just about to slip. To slip means that Fs equals Fs max, which is equal to mu sub s times N2. Okay, and we'll do that on Friday. So, And this, I'll just put up a little sort of schedule of what's happening over the next few weeks. We got a class on Friday. Reading week, I'm not going to be around for office hours. I'm doing some outreach stuff and things. Monday, we're back. And then Tuesday, we got the term test. Chapters 5, 6, 7, and 8. And I'll see you Friday.
Really quickly, I missed one last ed question that I liked.
Yeah, I don't think there's time.
Okay, we don't have time.
Yeah.
Sorry.
I'll do it next class, but thanks.